in this advanced conduction lecture series. So today is the lecture 15. So we have already come along a very long path. Now I thought that I would be completing the separation of variable chapter. I mean, not the separation of variable chapter, that is a topic of mathematics, but I thought that I would be completing various cases of conduction heat transfer equation solving by solving two more problems. But now I have a different thought that uh, I have planned it like that I will cover the fins first, and then I will go for a quasi-static conduction problem, that is a rod moving in a furnace, and then after that I will be solving some more types of problems other than the methods that we have already covered, that is the separation of variable and uh, superposition. Then I will finish up the course with the remaining two problems. Okay, so today we will start with the fins, right? Now let me put the lecture number. Okay, so the pencil has to be connected. I hope the pencil has charge. Oh my god, pencil is not charged yet. Okay, so up till the pencil is getting charged, let me talk about something that will help you in the semester. Those of you are going for gate, in the gate examination also it will help you. So those of you who are studying in M.Tech in any IIT or any IISc, see, you might be thinking that why this guy is leaving so many things for us, because you will not get any, I mean, you will get a minimal amount of repetition in the question paper. Okay, so maybe in your BTech you have the practice of solving the previous year question papers, and you are used to get those questions common in the examination. But in this level, in this M.Tech level, especially in IITs and IISc, you will not get that type of thing. So unless and until you develop your own solving and testing skill, you will not be able to score a good grade. That is why I do leave the things for you so that you can solve it by yourself. Okay, but having said that, I have also stated in my every video that if you are getting any type of doubt that why is this so, and I can solve it, I have tried it a lot and I can solve it. Even if one student puts a comment in the comment box, I will take that into account and I will make a separate video on that solution of the problem. So do that. And the aspirants of gate examination, for them, so you can skip various parts here. Obviously the separation of variable things and all, you can skip those. Okay, I have covered all the things, but let me tell you one thing that uh, see, nothing goes in vain. Okay, so everything you learn, it at least helps to develop your brain power. Okay, so many student asks many professor that I am a student of computer science, why do I need to study engineering mechanics? Obviously that will not help you in your professional career, but when you study engineering mechanics and solve a problem by your analytical thinking, then that thinking will help your brain muscles to grow. That will help you in solving any machine learning or deep learning problem. And having said that, for a mechanical engineer, if I mean, I have seen many mechanical engineers that will coding come in this subject. So accept one fact that you have to have a bit expertise in coding, not in the sense in which computer science students take it, but in a sense that, see, you can't do all the calculations, all the matrix operations, all the numerical operations by your hand. That is what uh, the thing CFD has come. So nowadays students are like, I will study the theory of CFD and I will operate the ANSYS, but I will not write code. So that is not CFD. Yes, in the previous era people were not having this much strong computers. So that is why they were like that, I have to do it by my own hand. They used to perform the iterations of the numerical operations by manually, I mean. So but in this era, when you are having strong computers, supercomputers, you have to code that, otherwise you will be behind in the competition. Okay, so that is the thing. I mean, don't be that much rigid. Okay, because things are changing, and if you are not changing, you will be torn away. Okay, so enough of gyan. Now let us move to the lecture, as the pencil has been charged. So this is lecture 15. Clear? So today we will start fins. So I will start from the very basics, because I have promised that I will be covering the gate topics also. So what are fins? We will be starting here, fins, and we also call it as fins, or what, extended surfaces. Extended surfaces. Clear? So what is that? That is nothing but, if you have any body like this, okay, maybe any cylindrical body like this, and maybe it is the case that any fluid is flowing here. Okay, so if this is the case, okay, so just give me 1 second, just let me check that if there is any alarm. Okay, actually my phone has so many alarms set, so if any alarm rings, then the video will be stopped. I will restart the video. Okay. Now fins are what? So maybe in a hot fluid is flowing. Okay, then I can have some extended surfaces like this. So the surfaces can be arranged like this, okay, throughout the body, cylindrical body, in a particular pattern, right? So when a hot fluid will flow through this, and here maybe I am having a cold ambient. Okay, so here I am having a cold ambient, right? So generally, I mean, naturally this will be the case, that heat will flow from this to this. Okay, now if you are supposed to increase the heat transfer, then what will you do? You have to either increase the H, that is the heat transfer coefficient. You can increase the area of heat transfer. So this area is area of heat transfer. That means you have to judge that in which area the heat transfer is happening. Area of heat transfer. Okay, and you can also play with the delta T. So delta T is not in our hand, that is already given by the problem. We can vary this, we can play with this H and this A somehow. Okay, now H you can control, obviously. I mean, if it is a natural convection, that is you don't have any external power source to augment the convection. And the second case can be, you have a fan here, so you have air flowing around this cylinder, this is air. Okay, then it is forced convection and the H will increase. Thusly you can play with H to augment your heat transfer. Now what if you can extend the surface area? Okay, so if you can extend the surface area, then also your heat transfer will increase, because what, Q is equals to HA delta T. So either you increase H or you increase A. So fins actually provide the body more surface area. Okay, but it can be the case that fins can also inhibit the heat transfer. Okay, it can also be the case. So that we will, I mean, see by some mathematical analysis that on which parameters the heat transfer from the fins will depend. Okay, and because fins are, uh, I mean, there is no compulsion that fins will always increase the heat transfer area. We have defined a parameter like fin effectiveness. That is, what is the heat transfer rate after having the fin and what is the heat transfer rate before having the fin, and we have to compare that. So the ratio of these two is nothing but the fin effectiveness, and naturally we want a fin effectiveness greater than 1. Okay, so let us see. So fin is an extended surface. Okay, so if we have to analyze a fin, so I will take up a general case first. Okay, uh, okay. So this is the body with which the fin is attached. Okay, and the fin has a shape like maybe this. Okay, so fin is having a shape like this. Then it is like this. Clear? It is attached to a body. So first let us set the coordinate axis. Okay, in this direction I will be having my x coordinate. In the perpendicular direction here I will be having y, and in this direction I will be having my z. And this is my origin. Okay, nice. Now see, I have considered it as a three-dimensional body. Okay, now think of the fact that when I can consider only heat transfer in x direction. Pause the video and think when I can do that, because I have told you that in the uh, actual practical field nobody will tell that this is a problem which can be considered as a one-dimensional problem. Okay, now let us see. So the length of the fin is given. This length is given as L, and the width is also given. Width is W, and the height is also given. Okay, so the height is 2h, or rather I can define it like this. This is h and this is h. Okay, I think the diagram is clear. Okay, so now what we will see is that what are the thermal resistances in different direction. Okay, so you see here what we will assume is our L is much greater than 2H and W. Okay. If it is so, then my W is very much small. So if my W is small, then my thermal resistance in Z direction will also be small, because thermal resistance is, is equal to L by K into A, right? So if W is small, my thermal resistance is Z direction is small. Similarly, if my 2H is small, then thermal resistance in Y direction is also small, right? So if those are small, see, if you have resistance is small, then I mean, what does the resistance do if you take the thermal network or you take the electrical network? So in electrical network, our purpose is to flow current, and for the flow of current we need to have a voltage drop, and actually the resistance is what which is causing the voltage drop. Similarly, here our primary objective is to flow heat. Now for the flow of the heat we need to have some temperature drop, which is caused by the thermal resistance. So if the thermal resistance is very high, then for the same flow of heat you need to have a higher temperature drop, and if the thermal resistance is very small, then for the same flow of heat you need to have a smaller resistance drop. Clear? So here the thermal resistances in Z and Y directions are small. Here the thermal resistances in Z and Y directions are small. That means I can say from this one that variation of temperature, I am writing T, in Z direction is negligible or small. Okay. And from this I can say variation of T in Y direction is small. Okay. That means I can say from these two arguments, okay, from this and this, T is almost constant in YZ plane, right? So another mathematical parameter can define it. Okay, this thing that if I can consider the variation of T in YZ plane constant or not. So that is bio number based on Y length scale and bio number based on Z length scale. So this will be what? This will be H into Y by K, and that is here the H into 2H. Okay, so let me term this height as capital H, because otherwise we will be getting confused with the heat transfer coefficient. So this is capital H. Clear? So this will be also capital H. Okay. And in Z direction it will be H into W by K. Okay. Now you see, what does your bio number say? Bio number is what? H into L by K. So that is nothing but L by K A into 1 by H A. I can write this, right? So this is conduction resistance R conduction by R convection, right? So if bio number is very small, that means my conduction resistance is very small compared to the convection resistance. Now if my conduction resistance is very small, then the same things actually can be concluded, that is, if my conduction resistance is very small compared to the convection resistance, that was the case when you can consider a body to be a, I mean, to be undergone to a lumped parameter analysis. In lumped parameter analysis, we take the fact into account that my temperature profile is constant throughout the body. Okay, so that is the thing. Here also I am putting the same argument, that is because the bio number in uh, bio number based on the y length scale and the z length scales are very small, so I am neglecting the temperature variation in the y and z length scale. So now I will put a very interesting fact in front of you, that is, I have also neglected for the three-dimensional block problem the heat transfer in the y and z direction. But there the reason was the y and z direction being very long, and here the reason is the y and z direction being very small. So these are very contradicting, like, right? So there the thing was that I have my thermal resistance so large that no heat can penetrate. So that is why I took that heat transfer is equal to 0. Now here heat transfer is not equal to 0. Heat transfer is there. But we are talking about the fact that the thermal resistance is so low that for the heat transfer the temperature variation here is almost negligible. So both of these arguments are very interesting and are not the same. In both the cases we are neglecting the temperature variation, but for the different reasons. Okay, and here you see, if the H is very high, if the H is very high, then we cannot neglect. Okay, then the bio number will be very large, and if the bio number is very large, then either our convection is very small or our conduction is very large. Okay, so I hope the argument is clear. So with this argument, now I will say we will only consider the x direction temperature variation, T variation. Okay, so let me again just copy this diagram and I will paste it here. Now I will start the analysis. Okay, so let us take a control volume first. I hope that you guys are acquainted with this type of analysis, because in your B.Tech, if you have done the basics of fin, I hope that at least some of you have not marked up only the formula and gone through the basic derivation. So if you have gone through the basic derivation, then you must be knowing this approach. Okay, so I will take a elemental volume, maybe with this color only. This is a bright color. Okay, so this is the elemental volume, and if I draw it fully, it will be something like this. Okay, okay, so I have drawn it. Now this is at a distance x. Okay, and the thickness is dx, clear? Okay, and I have the heat transfer coefficient in the air as H, clear, and the and the temperature is T ambient, the outside air temperature. Okay, so if I take this control volume, so what will be the energy interactions? Okay, so let us plot that, the energy interactions. Now let me draw it with another bright color, maybe with this one. Okay, so here, array, I changed this one. Okay, so here I will have q dot at x, and here from this face q dot x plus delta x. Okay, so let us consider this as delta x first, not dx. Okay, q dot x plus delta x will leave. Okay, and also for from throughout the area I will be having the convected heat. Okay, so q dot x, this much heat will be conducted through this phase. Okay, through this phase, clear, and q dot x plus delta x, this will be conducted through this phase, and the heat convection will be through this area, this area, this area, and this area. So total peripheral area, clear, that is this one, this one, this one, and this one, clear. So for this control volume, if I now write the energy balance on the CV, okay, so that will be what? Energy that is going in minus energy that is going out minus again energy that is going out by convection, that will be equal to 0. When it will be equal to 0? If it is steady state. So we are assuming steady state temperature profile. Okay, and there is no heat generation. Okay, now the same analysis can also be done with the differential formula that I have derived, the basic heat conduction equation. Okay, so then you have to integrate the heat conduction equation over this control volume, having delta x length, w width, and okay, so one more thing I have to define here, that is the maybe this one, the height. Okay, so this height will be a function of x, and maybe this will be some h of x. Okay, or let me term it as y, any y. Okay, and in the problem this will be given, that is the variation of y with x. So variation of y as a function of x, this is given. Okay, so in your undergraduate you have all you have only studied the constant cross section fin, right? Circular, rectangular, like that. Now here you have to study the varied cross sectional fin. Okay, okay, so now let us put the values. So what will be this? This will be h into a, total a of heat transfer, into T at x minus T ambient. T at x is what? Temperature at a distance x, and T is only a function of x. T is not a function of y and z. Now what will be this area? This area will be your perimeter into delta S, not delta x. Now what is delta x? See, if I zoom this part, then what will happen? it will be termed like somewhat this. Okay, actually it is a curved part, but if I take this delta x to be very small, then it is something like this. So this part and this part we will take. So if I draw it clearly here, now this part is your delta x, this part is your delta y, that means this part is your delta s. So I am talking about this part only. So this part is your delta s and this is your delta x. Okay, so if I draw it like this, so this is my triangle. Clear? So I will try to draw it here in a neat manner. So this is the thing and this is the small triangle. This small triangle has been enlarged here. Okay. Okay, so this will be perimeter into delta x. Now this perimeter is a function of x also. Okay, so let me write it, that is this perimeter which is a function of x into delta s. Now this delta s is what? Delta s is root over of delta x square plus delta y square. Okay, and if I take the delta x common, delta x square common rather, it will be delta y by delta x square plus 1. Okay, now then let us do the analysis. So here q dot x minus px delta x root over of delta y by square plus 1 is equal to 0, right? So I will take the limit delta x tends to 0 and I will divide the whole equation and I will take a minus common here. Okay, so in this expression also I will take the limit so delta y by delta x whole square, okay, is equal to 0. Now in the limit delta x tends to 0, this becomes d dx of q dot x, right, minus actually, and this will become what? Your px into dy dx whole square plus 1. Clear? I think I am not doing anything wrong. Okay, so then what we will be having from the Fourier's law of heat conduction, this will be minus k area that is a function of x again into dt dx minus p of x into this one. Clear? So if you further do the steps, then this minus and minus will be cancelled out and it will be plus. Now considering constant k, okay, it will be dA dx into dt dx plus k into a into d2t dx2, okay, minus px into this one. Okay, and this is equal to 0, and this line is true for constant K. Clear? Okay, so these things are very important. Okay, whenever you are writing an advanced level examination, you have to write all the assumptions. The assumption can be very obvious to you, but that can be not very obvious to a professor. If I become a professor, I will definitely deduct some marks on it. Okay, so by this time you guys may be now thinking that we are lucky enough to not get him as our professor, right? So joking. So let us continue. Now this is the governing equation that we are having. Okay, this is the governing equation. So what is the next step? Is the boundary conditions, right? Okay, so the boundary conditions. Now what will be the boundary condition? See, one boundary condition is that you know that what is the temperature at the base, and you don't know the heat transfer at the base, and at the base means what? Base means at x equal to 0. Okay, that is this part, base of the fin, and this part is called the tip of the fin. Okay, so at the base of the fin, q at x equal to 0 is not known. Okay, sorry, not 0, no, is not known, why? Because this is a fin, right? You need to enhance the heat transfer. You don't know that what will be the heat transfer. Now in any problem that can be given as a boundary condition, that is a valid boundary condition, that at x equal to 0 q dot x equal to 0 is given. That is a valid boundary condition, but practically speaking you know only the temperature at that point. Okay, so this can be a valid boundary condition, that this is given. So this is valid but not practical. Okay, from the point of view of fins. Okay, and you can have at x equal to 0, T at x equal to 0 is given some T base, some base temperature. Okay, then you can have the second boundary condition as your what? At, okay, now at the tip. So here I will be writing at the tip of the fin. Okay, now here many approximations can be taken. One is a long fin, that is if my L tends to infinity. Now, and infinity, I mean in terms of the engineering, infinity means very large compared to the other dimensions of the problem, very large. Okay, so if that is the case, then we can consider our T to be, T at L to be almost equal to T ambient. Okay, this is a very long fin approximation, and then we can have insulated tip. Okay, that is dt dx, or here you can write as dt dx, not del t del x, because t is only function of x, at x equal to L is equal to 0. And finally we can have the tip with natural convection. So there we will be having H into T of TL minus T ambient. Okay, that is equal to minus k dt dx at x equal to L. Okay. These three types of boundary conditions we can have in the tip. Okay. Also in the tip you can also mention the uh, heat transfer. Okay, that is also possible, but practically we don't do that. Okay. So now we have got the boundary condition and the governing equation. Okay. So let us solve the fin for the case that you have already studied in your B.Tech. So case 1. Okay. So this fin will not be a very large chapter to complete. Okay. We will take two cases, this constant cross section and one varying cross section. Now I am uh, giving you the chance to say your choice, that I mean what should be the varying cross section profile, that is the function of y, I mean y as a function of x. Should it be triangular, should it be a constant function like y equal to cx, and it can be a parabolic one, anything. So you give me that function. Obviously not all the functions will have an analytical solution. Okay, that you need to remember. So a constant function has an analytical solution, the parabolic function has an analytical solution, but I have not tried with the ellipse and all. Okay, so if you don't put any suggestion in the comment box, then I will go with the parabolic one. Okay, in any ways I will go with the parabolic one because that is important in terms of your exams. Okay, now case 1 is y is not a function of x. Okay, and that means your a is not a function of x, that means your perimeter is not a function of x. Okay, so y is h for all x. Clear? I hope you know this sign. This sign is for all. Okay, so that means the fin will be a rectangular fin, or a square fin is if h is equal to w, and it will be something like this. It will be something like this. Okay, so maybe this is your uh, base. Okay, so this is your base and this is your tip and this is your x direction. Clear? So now let me copy the governing equation. Okay, this is the governing equation. Now in this governing equation, this term is 0 because a is not a function of uh, x. Now this is a constant, and what will be that constant? That constant will be 2 into w plus h, w plus capital H, right? Because this is your 2h and this is your w. So this will be 2 into w plus 2h, not h actually. Okay, and again, because y is not a function of x, that means this will be 0, right? I think we are missing something in the governing equation, I think. And I know that what we are missing. We are missing this whole thing. I am very, very sorry. H into delta T. Arey yaar, what I am doing. So here I should have H into Tx minus Ta. Okay. Here also this should be this into H into Tx minus Ta. I am extremely sorry for this. Okay. H into Tx minus Ta. Again H into that is why I was thinking that this equation is like बहुत छोटा लग रहा है. It should be a bit longer. And here also in the final governing equation I should have that H into Tx minus Ta. Clear? Okay. So here you should have your H into Tx minus Ta. Okay. So what this will become? This will become Ka minus P, that is a constant, into H into T of x minus T of A is equal to 0. I think up till now, I mean by this time you have already pointed out that this was the governing equation that you studied in your B.Tech level. Okay. So this is Hp by Ka and this is Tx minus Ta. Now Ta is a constant, so I can define a variable theta is equal to Tx minus Ta. Okay. And if I apply this transformation, this will become del 2 theta del x2 minus, I will term this as m square into theta is equal to 0. And here m is what? Here my m is equal to Hp Ka whole to the power half. Okay. Now you have marked up this equation maybe in your gate, and moreover the solution, by this time you must know that how the solution is coming, that is C1 e to the power minus mx and plus C2 e to the power mx. Okay. So this is a solution, and now we have to put the boundary condition. So let us put the boundary condition of at, so T of x equal to L is equal to T of ambient. Okay, that means theta at x equal to L is equal to 0, right? So that means my 0 is equal to C1 e to the power minus ml. Okay, and we also know that this is not the mathematically correct boundary condition, because there should be t at x tends to infinity, my this is equal to Ta, at least my theta at x tends to infinity, because this is for a large fin. Okay, so effectively my L is also going towards infinity. Okay, so that means this will be 0 is equal to limit x tends to infinity e to the C1 e to the power minus mx plus C2 e to the power mx. Okay, so you see, if in this term if I put my x tends to infinity, then it can never be 0, this will shoot up. Okay, that means if this has to be true, then my C2 must be 0, because if this term is there in the equation, I cannot have this whole term is equal to 0. Okay, that means my theta is equal to C1 e to the power a minus mx. Okay, now how to find C1? For that, at x equal to 0, that is my base, so t of x equal to 0 is equal to tb. Similarly, theta at x equal to 0, I will have tb minus ta, and that I will term as theta b. Okay, that means my theta b is equal to c1 e to the power minus m into theta b, sorry, minus m into 0. So that means my c1 is equal to theta b. Clear? So that means my temperature profile is equal to theta b equal to this minus mx. In other words, my theta is what? T minus Ta. My theta b is what? Tb minus Ta, that is equal to e to the power minus mx. So this was the celebrated formula that you have marked up for years and years to get into IIT. But by this time you have got into IIT, now you cannot mug up any formula. If you mug up, then you will be doomed. Okay. So this is true for what? Constant cross-sectional area, constant properties, that is constant thermal conductivity, and long fin approximation. Okay. Now we define, okay, so now you have to find the heat transfer, total heat transfer from the fin. Okay. So if you have to find the total heat transfer from the fin, then what will be that? See, this is steady state, right? This is steady state. Then whatever heat is coming from the base, that has to be go out through the fin, through the whole fin. If it has to be steady state temperature, then whatever heat flux is going through the base, that has to be come out, right? That has to come out. Otherwise, the temperature will either decrease or increase if the heat transfer is not equal. So one option is, if you have to find the total heat transfer rate here, okay, that is the total heat transfer rate, then that will be equal to, you can integrate qx, not this one, yes, qx dx, but you can integrate small qx into dA all over the surface area. Okay, all over the surface area of the film. You can do it. Okay, because you know a as a function of x, here a is a constant. Okay, but so this dA will be what? Here this dA will be your perimeter into dx. Okay, you can do this. Now, and you also know this by your Fourier's law of heat conduction, this will be this one. Because you know this T, you know this T, that means you know this one, that means you can perform this integral. And another approach is, but that will give you the same answer, that is q dot at x equal to 0, and that is because this is at steady state. I have already explained to you the reason, right? Okay. Now this one will be equal to what? Okay, so this will be what? This will be area at the base, that is area at x equal to 0 into small q dot into at x equal to 0. Area at x equal to 0 is what? 2h into w, and this is what? Minus k dt dx dt dx at x equal to 0, right? So this is 2h into w and minus k I can take common. Now dt dx I have to found. So from this equation, okay, from this equation t is equal to what? So I will write this clearly. T is equal to tb minus ta, okay, into e to the power minus mx plus ta. This is equal to t of x. So this will be equal to 2hw minus k. Tb minus ta is a constant, it will be come out of the derivative. Ta is a constant, its derivative will be 0. This will be e to the power minus mx into minus m. This minus and minus will be cancelled out and will be plus. Now this will be 2hw, okay, into k. Now m is what? M is root over of hp by ka, and there is tb minus ta into e to the power minus x, and this derivative is we have to compute at x equal to 0. So this will be at x equal to 0. Now this will be equal to 2hw, okay, I can already cancel this out. So this whole term will boil down to what? Let us see. So 2hwk. Now h, so perimeter is what? 2h, okay, so let the perimeter be like that, and now area is what? Area is 2h into w, right? So I mean essentially this is the area and this is also the area, okay. So this term will boil down to root over of hpka. So the whole heat transfer is coming as root over of hpka into theta b, right, because it is tb minus ta, and this is the answer, okay. That means hpka into tb minus ta, okay. And so this was the thing for the long fin case, okay. Now let me define the very important parameters. The one is fin efficiency, okay, fin efficiency. So fin efficiency, it is what? That if this is my fin, okay, see here carefully, and this is my base and this is my tip. Now there will be some temperature drop from this base to this tip because this fin is having a finite thermal resistance or a finite thermal conductivity, okay. So if the case was like that, that the fin is having infinite thermal conductivity, that means zero thermal resistance, because thermal resistance is L by K, it is inversely proportional to the excuse me, thermal conductivity. So if the thermal conductivity shoots up to infinity, that means the thermal resistance has to go down to 0. Now I have already told you, for small thermal resistances we can neglect the temperature variation. So if this fin is having negligible thermal resistance, that is zero thermal resistance, that means the temperature drop from this end to this end will be 0, but there will be heat transfer, okay. Heat transfer will be there, but the temperature drop will be 0. So the fin will be at same temperature throughout, okay. I repeat again, because of having finite thermal resistance and that is having finite thermal conductivity, this fin is having some temperature drop from here to here, the temperature is decreasing throughout the fin. But now I am talking about an ideal case in which the fin is having zero thermal resistance and infinite thermal conductivity, because of which the fin is having the same temperature Tb, that is the base temperature, throughout the fin, okay. So therefore I can write that fin efficiency is the ratio of, so eta, that is the fin efficiency, okay. So that will be this will be actual total heat transfer obviously from the fin, because we are analyzing the fin, and by total heat transfer for the case of zero thermal resistance. Okay, so this thing, this denominator thing, this thing essentially means that T at Tx is equal to constant is equal to Tb, that is the base temperature, right, and that is equal to our actual total heat transfer is what we know, that is root over of HPKA into Tb minus Ta. Now if Tb is the total temperature, I mean everywhere on the fin surface the temperature is Tb, and we know that H is my heat transfer coefficient, so then that will be H into Tb minus Ta into A fin, right. Okay, so the battery of my phone is 15%. I have to complete it as soon as possible. So this will be HPKA, this will be here H. Now this will be cancelled out, this thing, okay, this and this will be cancelled out, and this will be H into A fin is what? Now total A fin is your again perimeter into length, right, perimeter into length, correct, okay, plus the area of tip actually, okay, but if we neglect this area of tip comparable to, compared to this perimeter into L, then this will become what, perimeter K A. Now this A is what, this A, okay, so this is, now we have to make some approximation, so let me write it in details. This will be H. Now this perimeter is what, this perimeter is the same perimeter, okay, and K into this H is 2HW, right. Now here I have A, P into L plus 2HW, right, okay. So now what I can do is, obviously I will be having 1 by root H here, so let that be aside, and root K will be here also, so I will be having here P into 2H plus W, okay, right, and here if I take the L common, this will be 2HW by L, okay, if I take the L common here, clear. Now you see that I know that both H comma W is much less than L, much less than L. That means compared to this perimeter P, I can neglect this, okay. So I can tell that my this perimeter is much greater than this, okay. So that will be equal to my root over of K by H into P 2HW, clear, root over of that by root over of P, I have 1 by L here, okay, and here I did not have that this root over, so that means this will become K by H, right, 1 P will be here and this 2HW will be here, so this is this, and this is what, 1 by M into L. Now I am sure that 99% of you have forgotten that how this comes, that is this efficiency of a fin having a very long length, that is we all know, that is 1 by ml. Sorry about that, 1 by ml. Okay, we have marked up with a great pride and we have scored a very good rank in GATE. Okay, but that is the fallacy of GATE. The boys or girls who crack GATE, they are not the great mechanical engineers, they are good examination crackers. Okay, so I mean, not necessarily they are the good mechanical engineers, there can be. Now you must be clear with all these things, that how I am getting that 1 by ml, because if I don't have this hw much less than l, then all this analysis will be failed. Okay, so this is the fin efficiency for a long tip case, long fin case. Now the second parameter, that is the fin effectiveness. Fin effectiveness. Okay, so now those of you who are in M.Tech and thinking that I am in M.Tech, I don't need to do these things, believe me, there is nowhere written that the professor cannot give you the basic things. And if he is giving the basic things, uh, he will not teach those in the class, because he will be expecting from you that you are already aware of the basic undergraduate heat transfer. Okay, then he can ask you the thing. So he will give you the variation of the cross section of the fin, that case that I will be covering in the next lecture, and then he will ask you that what will be the total heat transfer. Then you have to use this funda. So if you were that student that who has marked up this formula of total heat transfer, that is this one, then you, I mean, if you don't know that how this came, then you will not be able to solve that question, that is find out the total heat transfer for a fin having variational cross sectional area. But if you know the funda, that you know that this was the concept, that how I got that, or this was the concept for steady state, that how I got the total heat transfer rate, then you can do it for any case. Similarly, if he asks you, if the professor asks you that find out the efficiency of the fin, then if you know the funda, that I mean, what is the uh, approach and what is the definition of the fin efficiency, then you can find. Okay, now what is the fin effectiveness? Now fin effectiveness we denote it by epsilon. I have talked about it in the beginning of the lecture, that is, if my fin was not there, then what was my heat transfer rate, and if my fin is now there, then what is my heat transfer rate now. So the ratio of these two. So this is actual, or I should write heat transfer with the fin, clear, and heat transfer without the fin. Okay, so let's try to find this. Now heat transfer with the fin is HPK root over of that TB minus TA, and uh, heat transfer without the fin is what? That is area of base into H into TB minus TA, right? Now if I perform this, so then this will be H into P into K. Now this area is what? This area is same as the area of base for a constant cross section fin, right? So H, this will be the thing, and now this will be what? K and P are there, this will be H and AB root over of this, right? So this was the effectiveness for this, and this should be greater than 1, otherwise you will be fired from your job. you have designed a fin which is inhibiting the heat transfer. Okay. Now don't only mug up this formula, you see that on which terms this is this thing is, I mean, depending, that is the effectiveness. Okay, see, if you have a fin in air and a fin in water, okay, and both are having the forced convection, so then in which case the fin will be more effective. If I say you that my fin is in water, the surrounding is water and the surrounding is air, then in which case the fin will be more effective. So how can you say that? So with the change in the medium, this H will be changed, right? This H will be changed. So for the water, I think the H will be more, okay, and because of that only the fin will be less effective in water and more effective in air. Okay. Similarly, if I give you two fins having same cross sectional area, but this H and W is varying, then how can you find that which fin is more efficient? So fin efficiency is dependent on 1 by m into L, and that means L is same for both the fins, but with the perimeter by area ratio, so fin efficiency is dependent on what? Area by perimeter, right? Fin efficiency. So this is my fin efficiency, that is proportional to 1 by m, is proportional to 1 by root over of Hp by Ka. That means my fin efficiency is proportional to A by P. More, I mean, specifically root over of A by P. So you have to judge the A by P, that is the cross sectional area by P, okay, for a constant cross sectional fin. Okay. Now we all know that, I mean, what is the temperature profile theta for a insulated case, insulated fin tip. Then what is the efficiency for a insulated fin, and what is the effective net for a insulated fin. So for that you have to just alter the boundary conditions. Okay, so I will not do that in this class, okay, because see, the objective of this course is not to teach you the mathematics. The moment you know the governing equation and the boundary conditions, you can do it by mathematics. And even if you cannot do this, your job is to formulate the problem, your job is to model the problem. The basic job of an engineer is to model and simplify the problem. The moment you give the equation, then the job of solving the equation is for the mathematician. Okay. Now if the mathematician says you that no analytical solution is possible, then as an engineer you have to think that how can I simplify the problem more so that I can have an analytical solution. Okay. So this insulated fin tip case, that cos HML term comes, and this theta and this eta is, as far as I remember, tan hyperbolic H ml by ml, and this is 1 and this is Kp by Ha into tan H ml, as far as I remember. And this is, I think, the total heat transfer rate is theta b into HPKA into tan HML. So everywhere you have to multiply that thing, and this expression, I think, as far as I remember, that was having the term cos HML. Okay, I don't I mean remember it. And for the convected thing, for the convected, I mean for the boundary condition where you are having the mixed boundary condition, that is the heat that is convected through the solid that is coming out from the tip through the convection. So for that there was a method called length correction, LENGT, it's length correction. Okay. So this length correction will do what? It will convert the convection or tip having mixed boundary condition to insulated tip. Insulated tip. Okay, and how I will get this? I will get this by converting L as L corrected, so that will be, or maybe my L dash, where my L dash is L plus L corrected. Okay, now this L corrected was calculated to be area of the fin, total area of the fin by the perimeter of the fin. Okay, so for a circular fin, this will be, I think, R only for a circular fin. For a rectangular fin, this will be for area of fin is 2 into H into W plus perimeter into length, right, by perimeter. So this perimeter will have what? 2HW plus 2H plus W plus L. Okay. So now if we say that now if by anything you can say, what you can say, area by perimeter, yes, that is correct. Now this will be the actual expression, this will be the actual expression for the length correction. Okay, so this is a engineering approach to simplify the problem, that is because the convective boundary condition at the tip, that is a very complex boundary condition in terms of mathematics. So to convert it into a simplified boundary condition, we say that we increase the tip length, we increase the length of the fin, and we say that the tip has become insulated. Okay, almost insulated, that is the heat transfer is almost zero. Okay, another thing, that when can you consider a fin to be long enough? When can you consider the fin to be long enough? So for that you can do one thing, that is you consider the actual fin with the convective boundary condition. Okay, so maybe Q dot convective boundary condition, that is the most general boundary condition, that is the most practical boundary condition, and you equate it to the Q long fin. Okay, with the Q long fin. Okay, but here the length is not coming. So where the length is coming? Where the length is coming? The length is coming at efficiency. So efficiency for convective boundary condition, you equate it to the efficiency of long fin. Okay, and you do it by efficiency of long fin is what? 1 by A into L, or M into L. I have done it M into L, right? So if your L is of the order of what? L is of the order of 1 by M into eta of convective boundary condition. If L is order of this, then you can consider your L to be sufficiently long. Okay, and you can also consider this 1 by ml of the order of tan h ml, okay, by ml. So that is, you are saying that I am equating the long fin efficiency with the insulated fin efficiency. So by that, if you compare this also, then you see my tan h ml should be of the order of 1. So you have to find that L equals to L, for what value of L my tan H ml is of the order of 1. So for that also you can consider the fin to be long enough. So you have to compare the expressions, okay, that is, it is the limiting length at which you are, so it is like the transition from laminar to turbulent for a fluid. So there is a critical Reynolds number around which we are saying the flow is under transition from laminar to turbulent. Okay, it is the same thing, that is, there are two extreme cases. One is a long fin case, another is a convected boundary case when you are not considering the fin to be long enough. So for which length L, it is at the critical position that it can be considered also convective, also it can be considered long enough that I can apply the long fin approximation. So that is the concept. Okay, so we do it by comparing the fin efficiencies for different conditions. Okay, now you can convert the fin from a convective boundary condition from a insulated fin tip. Now whenever you can convert that, you can use that efficiency, that tan H ml by ml, and you compare that with 1 by ml. So by comparing that equation you can get a L. So that L will denote that critical length at which the fin can be approximated as the insulated fin tip also, as the long fin tip also. But if the L is much greater than that critical length, then you are supposed to consider the fin with the long length consideration. I think I am clear. I will be repeating this once more. Your objective is, that is, my long length consideration is the simplest case in terms of mathematics. So if I can consider all the fin problems having a very long length, then it will be much simpler. But how can I decide as an engineer that if my long length approximation is applicable or not? How can I decide that? That you can decide by comparing the efficiency of the long fin approximation and the efficiency of the practical approximation. That is the practical thing, that is the most practical thing, is the convective boundary condition. You can convert the convective boundary condition into the insulated fin tip, then you can compare the insulated fin tip efficiency with the efficiency of the long fin, and the M will be same for both because M is HPKA. So this HPKA is same for both the cases. You are approximating, you are seeing that for which length these two cases, the long length approximation and the insulated fin approximation, are almost equal. Then you can go either anyway. I mean, you can go by either way, either by the long length approximation or by the insulated fin. But if your length is much greater than that, then you must go through the long length approximation, because your insulated fin tip will be a complication, will be an unnecessary complication there. Okay, I hope I am clear. So put the doubts in the comment box, nothing much to say, and in the next lecture we will be ending up with the fin thing by solving a parabolic cross section, that is y equal to some